Okay, so welcome to this video where we will look at related rates. I'll probably go relatively quickly, and the idea is that I'll go faster than a lecture, but you can pause me when you need to. Okay, so what this section is about is when you have two different variables that are changing in time, but there's a kind of a relationship between them. So as an example, if you're pumping a balloon, as you pump air into the balloon, the volume increases and also the radius increases. And the question is, what is the relationship between those rates of change? Now, on the face of it, it's a little bit difficult. Like if it says, okay, if the volume is increasing by 1 cubic meter per second, how fast is the radius changing? It's a little bit difficult. Now what I'll do is we'll talk about a spherical balloon here. So I'll just draw a little schematic of it. Something like this. And let's say this is the radius. And I'm going to write r is a function of t. And what this is signifying is that the radius is changing with time. And also the volume is changing in time. Now, the way that we kind of deal with this as such, now eventually what we're going to do is we're just going to kind of have this kind of funny thing where you write something down, but we'll show where it comes from here. So you have the volume is a function of time, but if you think about what does the volume of a sphere depend on, well, all it really depends on is the radius. So what we have is that the volume is a function of radius. Now we can come over here, it's no problem. We can write down that the volume in fact is 4/3 pi r cubed. But in this question, what we have is that the volume depends on the radius, but the radius depends on the time. And what we can do is we can just differentiate both sides with respect to t and just see what happens. So if I do that, okay, the derivative of volume is dv dt. Now, say in the question of pumping a balloon, that would be something that you know. The air that you're pumping into it, however much is being blown in, that's essentially the rate of change of volume. If you blow in whatever 10 cubic centimeters per second, that's what dv dt is. Now, when we're differentiating this, we're going to have to do a little bit of a chain rule. I'm going to write above the chain rule as I do it. So when I'm working with this is what's called a composition. Now we can talk about it on various different levels. You can talk about it outside and inside. That's what I'll talk about. But actually what's happening is you have an input time into a function radius and you get an output, and then the output of that radius function becomes an input for another. It's called a composition. And to differentiate such functions you need the chain rule. Now I like outside inside, so I'm going to write it outside function as a function of inside. And what the chain rule says, to differentiate outside a function where it's the inside isn't a function of x, well, it is a function of x, but it's not just x. The chain rule says you must differentiate the outside. The chain rule says you must evaluate this at the inside, and then you must multiply by the derivative of what's inside. And we're going to have a similar story here. So let's see what it says. So differentiate the outside, so that's v dashed. Evaluate it at the inside, which is just r. And then times the derivative of what's inside. And the derivative of radius with respect to time is dr dt. And so this is dv dt is equal to this v dashed r by dr dt. What we might do is we might just tidy that up over here. This is dv dt. This is the derivative of velocity with respect to radius. Excuse me, not velocity, volume. This is the derivative of volume with respect to radius times dr dt. And actually, this is the same thing we actually did in the previous chapter to derive the formula for parametric differentiation. I'll just show you where that actually, can I see where it comes from? So say for example in the previous question I could say to you, okay, volume is a function of time, radius is a function of time, and then you can think about volume being plotted versus radius, and that would be a parametric function. And from the previous chapter you might be tempted to write down dv dr, and you know that if it's a parametric function you differentiate v with respect to t and differentiate r with respect to t. And if you multiply both sides by dr dt you get this. But actually what we did in the previous chapter is we did something like this to get here. Now what I want to just focus in on, you don't want to have to derive this like we're doing all the time. So what you're going to do is, in a question like this, you're going to identify a number of variables. So for example here you've got volume, radius and time, and what you do is you pick the most complicated one and differentiate that with respect to time. So volume would be considered more complicated than radius because volume is a function of radius. Kind of if you know the radius you easily know the volume, so volume is more complicated. So you take that complicated function or variable and differentiate it with respect to t. Now the thing I'm going to do next doesn't actually make any sense, but the work here and here shows that it is actually valid. So what you do now is you spread this thing out and write it as dv dt, and then you bring in the other variable, which in this case is radius. So you write dr, and the idea is that dr divided by dr, well, like, I mean, how would you make sense of this? Dr divided by dr is 1, so this is just dv dt. And if you ask yourself then, why is this right? Well, you can say, oh, it's a chain rule or whatever, but the big story is that it's coming from this. This is the same as this. So what it's saying is that if essentially when you have, say, y and some other function v and both functions of t, what you want to do is take the most complicated thing. Now why is y more complicated? I'm just saying suppose it is. Differentiate the complicated thing with respect to t, and then see this spreading out, dy dt, and then just put in the other variable. The other thing that's worth mentioning at this time, so yeah, well actually I can do this in English. So the units of dy dx. So, well, there's different things we can go about this, but ultimately I think we'll take, okay, so this is a rate of change of y with respect to x. So this is the same as the units of a change in y over a change in x. So for example, slow this down for a second. Think about the rate of change of distance with respect to time. The rate of change of distance with respect to time is nothing but velocity. And what are the units of velocity? Well, say it's miles per hour. A change in distance, miles per a change in time, this thing. And of course, if you have a change in time, say 10 seconds, well, that's going to be measured in the same units as time itself. So the units of dy dx would be the units of y divided by x. So the example of velocity, the rate of change of displacement with respect to time is meters per second or miles per hour, whatever you want. Okay. Now all it's saying below here actually is just if you wanted, you could, you know, because this is related, so you can go from the parametric thing to this, and you can go from this to the parametric. It's kind of just saying if you didn't want to learn this, you could do this. Personally, I think this is easier for the previous section, but in theory you could say, okay, I've got x, I've got y, they're both functions of time. Now you're going to just decide that y is more complicated, and that's a kind of a difficult question to address, but let's say you did. So you just said dy dx, sorry, you differentiate the complicated thing with respect to t, spread this out, and then put in the other variable, which we're saying x. So in terms of the variables knocking around for a parametrically defined function, you have y, x, and t. Okay, So I put in the other variable here, which is, in this case, now you don't put x and x, dx and dx. And then in the previous section, remember you're interested in dy dx, so you just want to solve for dy dx. So you divide both sides by dx dt, and you get something that is familiar from the previous section. So dy dx equal to, divide both sides by dx dt, you'll get dy dt divided by dx dt. Now a lot of the time here what you're doing is you're treating these derivative things as fractions. Now they're not actually fractions, but it turns out that for, up to a certain point, if you treat them like fractions, everything works. So for example, if you have dv du and that doesn't necessarily make sense to you, so for example, we'll just do an example down here. Well, I'll do it down here in a second. It'll be, well, what happens if I don't know what the most complicated function is? How do I get out of it? Well, it turns out now you might look at this and go, what? Well, it's kind of similar. Now it's different stuff. There's a lot of heavy maths saying that these two things are the same, but you can treat them kind of like fractions. That 2/3 is the same as 1/3/2. Now, we don't like fractions in our fractions, but maybe just to show you that these are indeed equal. Say you don't like this little 2 here, well, multiply the bottom by 2, that will get rid of it. Now you've changed this thing here, but multiply the top by 2 as well, and this thing is equal to 1, that doesn't change it. So this thing here, 1/3/2 by 2/2, is the same as 1/3/2. So maybe we'll just put a little question mark on this equals. Maybe you're a bit Scooby-Doobious, so forget about the 2/3 for a moment. Okay, and okay, where are we? So 2 by 1 is 2, and then the 2 divided by 2 is 1 by 3 is 3. So if you've got 1/3/2, okay, you can multiply it by 1 and get 2/3. And multiplying by 1 doesn't change it, so that means 1/3/2 is equal to 2/3. Similar story here. We'll see how this happens. So say for example with the example of the balloon with the radius and the volume, suppose you say, oh, I know I need to differentiate the most complicated thing with respect to time, but maybe you just decide, oh, radius is more complicated. Say if you do that, what happens? So it will be okay. What happens is as follows. So you're saying, okay, I'm going to differentiate r with respect to t. It's no problem, absolutely no problem. And you get dr, you spread this out, dt, and then you bring in the other variable, which is dv. Okay, and this is all okay. dr dt. Now here we have to actually, we must emphasize something. We have mentioned this in probably the previous lecture last Tuesday in CIT, but we said, okay, we've got derivatives, and these are slopes of tangents, but we also said that derivatives are rates of change. So you have to know this. So for example, this is the rate of change of radius. Now if it's with respect to time, usually you just say, oh, the rate of change is automatically with respect to time, but you could include it. So w or t means with respect to time. Now what does that mean? Well, what it means is it's basically it's an instantaneous rate of change. I don't want to get too much into the weeds on it, but basically you're saying that, okay, if the time changes by 1 unit, the radius will change by dr dt. So it's like how much the radius changes in time. It's the rate of change of radius with respect to time. And there's two things you have to be able to do in this module and any kind of engineering maths. As soon as you hear derivative, you're thinking rate of change, you're thinking slope of tangent. As soon as you hear slope of tangent, you're thinking derivative. As soon as you're hearing rate of change, you're thinking derivative. These are all the same things. So we might just do a little thing down the bottom. As soon as you see a dy dx, this is a rate of change. And as soon as you see rate of change, you're thinking dy dx. Now this, as I said, is rate of change of y with respect to x. And then as soon as you see derivative, that is, I'm just going to write slope here, really it means slope of the tangent. and as soon as you hear a slope of the tangent, you need to hear dy dx. If this isn't kind of burned into your brain, you're kind of in trouble here. Okay, now we're pretty much ready to go on to examples. This is all of the theory here. We'll do a number of examples in a separate thing. The main thing is forming this equation, and we also, this thing down the bottom, that we understand that this is rate of change, the derivative is rate of change. We also need to be able to differentiate things, and then also the units finally are going to come in. Okay,